right? I think I have to dismiss this thing too. And the color ordered amplitude multiplying it, so which has, of course, the same symmetries as the trace. And in a sense, what we're going to be looking for is understanding if there's more structure, some of which at tree level, of course, is very, very classic by now, but other things beyond tree level are not. So, and again, all momenta are taken to be outgoing, and here the momenta we want to understand is generically complex. So yes, the spinors we usually take to be complex, but usually not the momenta. Here I want you to be thinking of the momenta as complex too. So at this stage we have n-1 factorial over 2 different amplitudes, and we're going to be chopping that down as we go over. So, of course, the classic formula for MHV, same denominator is actually the one that we'll be focusing on. So we'll be focusing on the all plus amplitudes. And the younger people in the audience probably know this as the Park-Taylor formula, but they may not know that this was not what was written down by Park and Taylor, unless you've gone back to read the original paper. This form was actually written down by Mangano, Xu, and Park, and actually for Fei's benefit, Xu is one of the first people who came out after the Cultural Revolution and wrote a really amazing paper, literally a couple years after the universities reopened in China. So, as we all know, these different color-ordered amplitudes are not all independent, and the Yang-Mills symmetry is reflected in linear identities between them. And as we'll be seeing, there's other unknown symmetries that are reflected in identities between them as well. So, simplest example is photon decoupling. If I call on a random member of the audience, would you be able to say what that is? All right, let me go through it very quickly. So you could, of course, have not SUN, but UN. Then, of course, the amplitude has to vanish. Remember, there's no fermions here, so that the photon can't couple. So one of the charge matrices, let's say A1, we take to be the identity corresponding to U1, and then we take the coefficient of the trace of all the generators that are left. And that coefficient is now a sum, where the first leg corresponding to the identity is actually placed in all different places. And of course, that sum has to vanish. The coefficient of every different trace structure has to vanish. That's the famous photon decoupling identity. And it generalizes to the so-called Kleist-Keif identities, which actually Lance, when I was up in Santa Barbara, pointed out that they wrote them down, but didn't really fully prove them. And he did with Vittorio, so probably should have added that reference. Anyway, there's a general form involving the shuffle product. And the main point here is that it reduces us to n-2 factorial independent amplitudes. And this is independent of the helicity, and it holds at tree level. So that brings us to the subject of Syzygies, which some of you may have heard of in the context of integration by parts technology. And the origin of the word, it's a little bit of an unusual word. I think it's of Greek origin, but originally in English, it had to do with relations in astronomy, where you have nearly straight line configurations. And it's very popular these days to call on help from AI. So I thought, okay, for a more general definition, I went to one of the AI programs. I've forgotten exactly which right now. And it gave me this definition. I asked for a definition of syzygy, and it said in mathematics, it's an object that describes the relationship between elements of a left A module. Now, I'm sure that for the audience, that completely clarifies what I mean by syzygy, but for more pedestrian people like me, I thought maybe I should also give you the meaning in amplitudes, namely, a linear relation between different amplitudes whose elements are polynomials in the Mandelstam invariance. And that's the sense in which I'm going to use the word syzygy today. So think of it as a linear relation, but where the coefficients are not necessarily constants. So at tree level, we have the Kleist-Keif relations, and we also have relations that were invented here, actually, before the Baumick Institute existed, with, I guess they were both students of yours at the time? Yeah. With John Joseph and Henrik, and Henrik later on came to Saclay as a postdoc, where he wrote one of the other papers that I'm going to refer to here. So that was actually really the first example of non-trivial identities of this class, where the identities are in fact linear in the Mandelstam invariants. And these are, in this case, helicity-independent identities, and they have the general form where you sum over a set, and let's imagine the entire set of n-1 factorial over 2 permutations. So everything that's left that corresponds to the symmetries of the trace. And so there's a sum over amplitudes with some coefficients. And in the amplitudes, the permutation is really, it's really a function of the permutation. So if you want to know what the amplitude is for some other permutation, you just plug it into the function slots. That's not true for the coefficients for the Syzygies. There, sigma is just a label. It can be different functions for different permutations sigma. So for those of you who haven't seen it or haven't seen it recently, these are just examples. So that of course, the starting point was really the 4-point amplitude, and you multiply by some linear function of the momenta with two otherwise independent amplitudes that are left after using the photon decoupling identity. And indeed, you can see that the coefficient is not just related by permutations. It's for each permutation, there's a different functional form. Anyway, you multiply them times the amplitude, you get 0. It goes on to the 5-point, and then on to n-point. And you can derive it from color kinematics duality, but I would say that it's fair to say that the deeper algebraic origin is not yet known. There's some hidden property of scattering amplitudes and Yang-Mills theory that will tell us, will explain what these are really trying to tell us. And this reduces the number of independent amplitudes to n-3 factorial, and that was thought to be it for many years. This is like 2010, when I have that chronology right. So it's 15 years ago. And you can write a general form, but with some, again, there's the shuffle product, and then you have a certain kind of strange looking formula for what exactly the function is, this P of sigma. And this form is due to Bo-Feng and his collaborators. There's many forms. It just happens to be the one that I like the best. So what happens at one loop? Well, we again have a color decomposition. And now there are not only single trace structures multiplied by what you can think of as the trace of the identity, but also things that are explicitly double trace structures. So you have to sum over all the different structures. But inside each of those, the overall structure is the same. You start with all permutations of the n legs, and you divide out by the symmetries of the traces, which is generally speaking an overall reflection and independent cyclic transformations of the labels within each trace. And if the two traces happen to have the same length, also the exchange of the two traces. So there's some group theory factor, and then there's a one loop amplitude, and the coefficient of the single trace one is called the leading color, and these are called subleading color because when you turn them into differential cross sections, that's how the power counting in the number of colors goes. Now, there are identities which with Lance and Zvi, we wrote down many, many years ago. They're helicity independent, and they basically allow you to express all of the subleading color amplitudes in terms of the leading color ones. So in fact, everything that we're going to be talking about today is just in terms of the leading color ones. Now, of course, for most helicity configurations, there's non-trivial integrals. And even though a lot of the discussion that I'm going to go through can be extended, I believe it's much more complicated. And so one starts with the two exceptions. The all plus and the one minus are purely rational functions. And they're purely rational at one loop because they vanish at tree level. And that's something for which I would hope every well-trained Amplitudes graduate student should be able to give the supersymmetry argument. And you can also do it by factorization and then induction, which is actually more the spirit of today's talk. So as a reminder, the all plus amplitude actually was initially conjectured based on collinear limits, and then it was proven by some complicated recursive current methods by Greg Malone, and then later was we gave a BCFW derivation. Anyway, there's some relatively simple numerator factor, which is in fact free of spinor weights, and then otherwise the denominator is in fact exactly the part-Taylor one. So what's special about this amplitude from the point of view of today is that it's only two particle singularities. There's no multi-particle holes. So that makes it the factorization structure particularly simple. Okay, so we've already talked about the identities relating the subleading color to the leading color. And at first glance, that's it. You're not going to expect any more identities between the different leading color amplitudes. But as it turns out, such identities can arise. And so we should go and explore them a little bit. Before we explore them, though, we should maybe think a little bit about some of the motivations for hunting for these identities. So if you're imagining you're actually trying to do some prediction for LHC physics, and you're focused, for example, on computing at higher multiplicity, then if you have some identity which is given in terms of simple functions, then you can use that to compute the missing amplitudes. You compute a smaller subset, and then you compute everything from them. So that can give you fewer objects to compute. There's also, of course, the time honored in the amplitudes field, the fact that when you understand more about the structure, that can give you clues about how to do otherwise more complicated computations. And finally, something that is maybe a little bit hazy is the idea that this can perhaps give you some insight into alternative representations of quantum field theory. So maybe not so much this generation anymore, but my generation grew up kind of with the idea that quantum field theory was the same thing as path integrals. Path integrals were quantum field theory and vice versa. And that doesn't have to be true, and maybe won't succeed ultimately, but certainly there's been a valiant effort by a small subcommunity started by, I guess, Nima and Yara Trinka to think about an alternate formulation of quantum field theory in the language of the amplitude-hedron. And so here I'm going to suggest that one can have perhaps a family of constraints that tell you something about amplitudes in quantum field theory, and therefore about quantum field theory that paint a very complementary picture. And obviously one is here at square zero. So, but that's one of the other motivations. So in fact, while he was at Saclay, Henrik, together with two deans whose names you probably know, Emil and Poole, and one other dean whose name you should forget, found that there are syzygies with.
Like we should forget them.
Yes, and you can ask me privately why I would say that. So they found an additional set of syzygies with constant coefficients, and again, this thing is actually a shuffle product, but I transcribed faithfully what was in their paper, and this is the notation that they use. So there's I And the question you might ask is, how many identities did they find? So the number of identities they found is n minus 1 factorial over 2, minus this strange bracketed object, which is in fact called the unsigned Stirling number of the first kind. It's one of these, I think, gifts of 19th century combinatorial mathematics. Why Stirling looked at this originally, I have no idea. In any event, for the 5 point, for example, you find 6 identities. At the 6 point, you find 25. At the 7 point, you find 135. And that should be contrasted with 12 amplitudes you're starting with, 60, and 360. So it's a substantial fraction, but it's not everything yet.
How did they prove this formula? Can you?
Well, they kind of derived it and checked it, and then they checked it numerically up to some number of legs. I mean, they had some graphical intuition as to how it should come, and they might beg to, Henrik might beg to differ as to whether it's a derivation. I wouldn't say it's a derivation.
So there's
It's an observation.
So there's no like recursive like multi-line shift or PCFW type recursion.
Patience. No, they didn't give anything like that. So then they didn't, prove and didn't prove completeness. So in some twister theory, there's some anomaly cancellation condition that was computed by Kevin Costello, and he found that if you take the amplitude not in just pure Yang-Mills as I'm presenting it to you, but in a theory that has a matter content of 8 fundamental plus anti-fundamental and 1 anti-symmetric tensor plus anti-symmetric tensor conjugate, then this amplitude vanishes. So that tells you there's some group theory reason for these. It's maybe not exactly a group theory derivation, but there's some group theory reason. And Lance and his student Anthony Morales showed that this cancellation condition implies all of the degree 0. So degree 0 in the sense that the coefficients of the amplitudes in these identities are all polynomials of degree 0. So that is their constants. So this anomaly cancellation observation implies all the degree 0. And they also prove that this is the complete set of relations that you can get of this type. So there's unexpected relations for the all plus amplitude. These are different, and here in the context of one loop amplitudes, even for the rational ones, there are different sets of identities for the 1 minus than for the all plus. I'm not going to discuss the 1 minus, but a lot of what I'm saying would carry over. So you might wonder, though, I mean, is this everything? Are there going to be any analogs of the BCJ identities? So this, I guess, makes the slide unsafe to show in China, but we might hope for a little bit more. And in fact, there is a little bit more. So here, there's actually no syzygies of degree 1. So the BCJ is of degree 1. They're linear. But the Danes and Swede were able to find, again, by kind of hunting around in their diagrammatic motivation, they were able to find, this is in the case of the 5 point, they were able to find an identity that where the coefficients are quadratic. Okay. And so then what they said is that there are actually 4 independent ones at 5 point. So in fact, that brings us down to 2 independent amplitudes, which is actually the same as a tree level. Tree level, again, after BCJ, at the 5 point level, there would be 2 independent amplitudes. And they said they found 32 independent identities at 6 points, leaving 3 independent amplitudes. And you might try to guess where that pattern goes, but don't guess too soon because you'll get the wrong answer. So the question is there more to the story? And so I want to step back for a second and take a somewhat more abstract view. So let's go back to either tree level or the one loop all plus. And we start with a set of n-1 factorial over 2 amplitudes. Those are just what's left from the symmetries of the traces. So let's think about the all plus amplitudes because they have a simple structure. And let's multiply by the common spinor denominator of all of these amplitudes. That's just the product of the bracket spinor products. And once we've done that, we have a set of polynomials in the spinor products. And the next thing we can do is to multiply them by essentially the conjugate factor so as to remove the spinor weight. So we're making them invariant under the little group, and you can see that, of course, this thing is again is another polynomial. So we now have polynomials, a set of polynomials that are invariant to the little group, and so we can organize them into traces. The traces we can convert to combinations of invariants and Levi-Civita tensors. This is the Levi-Civita tensor contracted with 4 momenta. So the indices are the indices of the original momenta. And so, for example, if you have a trace of 2 of them, you just get an Sij. If you have a trace of 4 of them, then you get a certain combination of products of invariants and a Levi-Civita tensor. And if you have 6 of them, then it goes on, and you can. This is so classic, you can look it up, maybe even in the appendices of your Kane and Drell, but and certainly in Peskin and Schroeder.
So, but for higher point, you're assuming 4-dimensional external
Yes, so everything here is in 4-dimensional external kinematics, yes. So, so the next thing we can do, we in general will have Levi-Civita tensors with many different combinations of momenta contracted. So we can choose a basis of 4 momenta, for example, the first 4. And then all the momenta in these Levi-Civita contractions, we can re-express in terms of these 4 basis momenta. And so now when we re-express a momentum in terms of the basis momentum, again, they're going to be coefficients, which are ratios of Gram determinants. And so we can introduce new denominators that are built out of these Gram determinants, up to 4 of them. And now we multiply by the common denominator of all these new factors. And so now again, we have a set of polynomials. And each of these polynomials has one term which is purely built out of invariance. And the other term is linear in the Levi-Civita contraction of the 4 basis momenta. And the important point is this set of polynomials now has whatever identities we had for the original amplitudes, they hold for this set of polynomials as well. Okay, so what are these identities? Well, any 3 such polynomials have a syzygy, and we can show that just by constructing them explicitly. If you have these 3 polynomials, we form these 3 coefficients, and then this object is a syzygy for those 3 polynomials, and therefore it's a syzygy for the original amplitudes. So more generally, any set of our original amplitudes will have that number minus 2 syzygy, or phrased differently, whatever number we've started out, they're rational functions, we will end up with 2 independent amplitudes, and there's only 1 independent amplitude at 4 points because the Levi-Civita contraction vanishes identically, so that term goes away. So in fact, we should have expected a lot more identities than people have been hunting for or had been hunting for. So this thing is an existence proof. It gives us a number of identities that is a target for us to find. Now, this general argument, unfortunately, does not give us the syzygies that we want, because if we just run things through this machinery, we're going to get syzygies of a very high degree. And here is the number of external legs. You can make an estimate of what the ordered degree of the polynomial is going to be, and it's very high. So this is not what we want. And in fact, I didn't use anything special about amplitudes in this general argument. It's just the fact that it's a rational function of spinors with a well-defined phase spinor weight. So amplitudes, of course, are not arbitrary rational functions of spinors. There are a lot of things that are special about them. So we should use some of their special properties to try and understand what identities can come about. And of course, the thing that is, at least for purely rational functions, things that have no integral functions, the thing that's special about them is complex factorization. In a certain sense, in d dimensions, the all plus amplitudes would also have cuts, but so far we have not tried to exploit that. And it's until one goes to amplitudes actually have integral functions, it's probably not important. So for example, for the MHV amplitude, as for example, the angle product of n minus kn minus 1 and kn goes to 0, we get a factorization where there's a 3-point amplitude with those two legs attached, and then there's a pole contribution, and then the remaining legs are stuck in an n minus 1 point. And as I mentioned earlier, all plus amplitudes share the feature that they have only simple poles in these angle products. So let's try and exploit that. So we're trying to find all possible solutions of this equation where an now is the all plus amplitude, and we're looking for polynomials in the Mandel-Stam invariants, which are labeled but not functions in the strict sense of the permutation sigma. And moreover, we know how many we should expect to find. We need to find the right number so that we have exactly 2 independent amplitudes left over. And that target is actually quite helpful to have. So what we're going to do is we take the residue at the angle ij, and I'm going to introduce a little bit of notation. When we take that residue, that replaces the permutation sigma by what I call a sigma brev, which just replaces the I and j with a k. And of course, I and j have to be adjacent in the permutation for there to be a pole in the angle product. So this equation then turns into a double sum. So we actually can factorize the sum over this permutations into the permutation, the relevant permutations of the n minus 1 point amplitude. And of course, on that pole, we get a factorization of the into the n minus 1 point amplitude and a 3-point amplitude. There's a potential numerical factor of actually just a plus or minus 1 having to do with rearranging the permutations into canonical form, and our syzygy just carries over. And I've also gotten rid of a common overall factor. And of course, I'm taking the residue, so the factor of the pole itself disappears. The 1 over ij disappears. So we have this equation not just for a selected ij, but for all possible choices of I and j, which there's n times n minus 1 over 2. Okay, so it's the same 3-point amplitude that appears in every term, so we can just divide it out. And now we have an equation where we group this plus or this sign factor with the permutations, and we have to sum over the 2 choices of permutation that give rise to a given n minus permutation relevant to the n minus 1 point amplitude. And so this object in parentheses has to be a syzygy of the n minus 1 point amplitude. So we have an equation that says that a certain sum of the on the pole, a certain sum of the endpoint syzygies with certain factors which you can compute, I mean they're explicit factors, is it going to be equal to a combination of syzygies for the n minus 1 point amplitude. So that's this equation. We have this combination of the syzygies for the endpoint is equal to some combination of Syzygies for the n-1. So if this thing, as we'll see in the all plus case, this thing at the 4-point level always starts out as purely constants. In the case of the MHV, there would be one that's a purely constant, one that's linear. And so the coefficients can, in general, be polynomials. Actually, there's some fine print that they don't even have to be polynomials, but let's ignore that for a minute. And then that will build up the endpoint syzygies. So, of course, we have a lot of different poles, and we want these as functions of endpoint kinematics, not of n-1 point kinematics. So we have to extend this equation away from the pole, which we do by adding, and this is, you can think of this as an avatar for functions that vanish on the pole. And there's some subtleties associated with that, which I'm going to leave to the fine print or post seminar discussion. So this is a set of equations, which at least this object is a polynomial, and it turns out that for most purposes, we can take the f and the c to be polynomials as well. There's a question of the behavior that's not fixed at any of the poles, the behavior in infinity, and you can impose that analytically via BCFW shift, or it turns out to be more convenient to impose it numerically. So these are not equations that you can solve in the usual kind of way by Gaussian elimination, because then you would not be guaranteed of getting polynomial solutions. So how do you actually go about solving them? Well, the first instinct is to just do linear algebra. So one writes down a general ansatz. So it could be an ansatz where the coefficients in the syzygy are constant, and you're looking for, or it could be where you write down an ansatz where they could be a polynomial of degree 1 or degree 2, and so on and so forth. And then the coefficients are things that you solve for. And so you would put in the ansatz, and then you generate many momentum configurations. And for the larger ones, then you want to use finite field techniques. And this is something which is perfectly feasible when the multiplicity is not too large, and in particular also when the degree of the polynomials is not too high. But you are dealing with matrices that very quickly get to be fairly large dimension, and this thing grows as n to the n, which is why it's kind of restricted to low multiplicity. So this was as I think one of the rappers in the chopstick raptors in QCD Meets Gravity said, it's simple, but is not necessarily easy. So there's another approach which requires a very short lesson, because I imagine most people here are not conversant with the computational algebraic geometry. And yeah, I think there are no native speakers of this language in the audience. And I will be very disappointed, actually, if someone without Googling doesn't tell me what language it is by the end of the seminar. So actually, how many people here are fluent in computational algebraic geometry, Grosvenor bases, and all that? How many are not? Some people are asleep already. Okay. So we have a set of polynomial equations in some variables, and the kind of one-line summary of everything I'm going to say is that this is a generalization of the ideas of synthetic division in the single variable case that everyone learned in high school, but everything is much more complicated when you go to multiple variables. So the framework is that we start out with some set of basis polynomials or generators, and the coefficients could be numbers or rational functions of other variables. And we want to consider all the polynomials that are built out of them. And this is called the ideal that's generated by the generators, by our basis polynomial. And In our case, we're actually starting with vectors, which the mathematicians in this context call modules of polynomials. And these objects are the coefficients. If we have our unknowns, for example, the actual syzygies, their coefficients are going to be these vectors. Those are going to be the generators that we're interested in.
Sorry, at this point, do you have any constraints on the degree of the polynomials you're looking
No.
at? So you're doing like all orders?
All orders. And I'll come back to make some comments about the computational issues, but one of the advantages of doing the Grosvenor approach is that actually whatever syzygies are, whatever degrees they are, the Syzygy code will produce them. So, in fact, in our context, what we want to ask is what are the syzygies of our basis vectors? Those would be the candidate solutions for the syzygies of amplitudes. So, in order to answer it, we need to choose an ordering. That's the key point where there's a distinction between single variable and multivariate. And so if you ever hear people mentioning the words, degree reverse lexicographic, that's exactly in this context. That's a kind of ordering of these monomials where in that case you choose the overall degree first and then the reverse by the lexical ordering of the elements. Then you build something called a Grosvenor basis. And let's see, how many people here are graduate students? Okay, so actually here the comment is really very well placed. So generally, things end up getting named after the people who did them, or maybe the people who worked on them last. But the Grosvenor basis actually was not invented by a guy named Grosvenor. It was invented by a guy named Buchberger, and Buchberger's thesis advisor was Grosvenor, so he named it after his thesis advisor. So I guess there's maybe a lesson there for the graduate students. So he gave an algorithm, and then one of the great ongoing subjects in computational algebraic geometry is finding better algorithms for finding this Grosvenor basis from some set of generators. But it's a special set of generators that allows us to answer these kinds of questions and many others in a very straightforward way. In particular, syzygies are elementary in terms of the Grosvenor basis. And they can be found by a construction similar to the argument I gave for the existence. And then in order to translate into the original vectors, you use something called the cofactor matrix, which you can build at the same time that you're building the Grosvenor basis. And this is all implemented in functions in Singular is the computer algebraic system that I happen to use, but there are others. And so basically the finding the syzygies in Singular is just you run a single command. I mean, there's a whole mathematical interface and setup stuff, but you're basically running a single function. And that function will provide the complete list of syzygies of all degrees. Or more strictly speaking, the generators of the syzygy module, because if you have a syzygy, obviously you can multiply it by some other polynomial and that still gives you a syzygy. Now, not all of the syzygies that you get, first of all, satisfy in the all plus case, they do end up satisfying the infinity constraint, but that's not true in general. And they're not all irreducible in the sense that some of them can be linear combinations, not in the Grosvenor sense, but in the ordinary linear algebra sense of other syzygies. So you have to do a little bit of work to prune the results that you get. You also don't necessarily get solutions in the simplest form. And so there's clearly, I mean, it's a brute force mechanical kind of procedure. So there's some human work that is still involved in getting some of the simplified results that I'm going to show you. So in the 5-point case, from this procedure, you find the 6 degree 0 that correspond to the Swedish-Danish collaboration, and also Lance and Anthony. And then you find 4 degree 2, which again corresponds to the ones that were found by Henrik and his friends. At the 6-point level, you find 25 degree zero. Again, that matches. At 7 point, you find 135 degree zero, which matches the results. In the 6-point case, as you now will have been expecting from the general argument, you find 33. So they found 32, and you find 33, which leaves you with 2 independent amplitudes. So you now know that, in a sense, let's say if you're doing it by linear algebra and you start at degree 0 and then you do degree 2, we haven't found this number. We know we have to go to higher degree. And I mean, in the Syzygy approach, in the computational algebraic geometry approach, you would have come up with them, right? Again, in the 7-point case, you find 223 degree 2 ones, which corresponds to leaving you with 2 independent amplitudes. So,
have you seen at any point that there's a like non-trivial degree like 4?
So we haven't done an exhaustive study, but and also the factorization equations. So the factorization technology is not fully developed for that, but you can do some exploratory studies with numerical linear algebra. And so for the NMHV at tree level, you find that there 6 points. You find that there's 1 or 2 degree 4 Syzygies. And my conjecture is that the complexity of the factorization is linked then to the fact that there's multi-particle poles is linked to the higher degree Syzygies. Also, this is going a little bit far afield, and it's also work that is not fully finished, but where all of this started was actually looking at the Syzygies of the rational terms in 2-loop all plus amplitudes, where they're unexpected identities, and that then, by a long and very complicated, tortuous route, brought us to this point. So if you look, for example, in the 5-point case, you can, whatever comes out of the Swedish-Danish paper is kind of random looking, and what comes out of the computational algebraic geometry is kind of random looking, but you can simplify it to a form where there's a nice kind of symmetrical looking structure, and also where you have only 5 non-zero entries. So there's only a subset for any given Syzygy is only a subset of the permutations that are really involved. And in fact, it turns out that basically using the symmetries, you can generate, in all the cases that we've looked at, you can generate the identities from a smaller set. So basically you permute the legs, you start with 1 identity on some set of legs, and then you permute the legs, and then that gives you the remaining set of identities. In the 5-point case, you actually can do this with just 2 generators. 6-point case, depending on exactly how you do it, you need somewhere between 2 and 4 generators. And in general, as the number of multiplicity grows, you need more generators, but the number of generators is still small compared to the number of identities. So as you might already have been expecting, because the factorization equations that I wrote down also apply to MHV amplitudes, there are also additional equations at tree level. So at 4 and 5 points, you're already down to 1 and 2 amplitudes just using Kleist-Keith and BCJ, so there's nothing new, and in fact, you don't find anything. At 6 points, this machinery, if you just run it through, you find all the known Kleist-Keith and BCJ identities, or you find linear combinations in those more accurate. And you also find an additional set of 4 degree 2 identities for the 6 point and 22 of them for the 7 point. And here, it turns out that you can actually write down a single generator for these new quadratic identities. That's actually quite simple. So you have, let's see here, 1, 2, 3, 4, 5 non-zero elements, and the remaining 55 elements are 0. And there's a slightly more complicated, but not vastly more complicated, again, single generator in the 7 point case. And whether that pattern continues to higher order, we don't know yet. But there's clearly a lot of simplicity. So I'm going to take just a couple of minutes to talk about another class of syzygies that most people know about, the simplest case of it. So now let's suppose we go from Yang-Mills, pure Yang-Mills, to thinking about Yang-Mills and also gravity at the same time. So gravity, of course, is in terms of the spinor phase weight is the square of Yang-Mills. So if I'm going to be looking for something, an identity that involves just Mandelstam invariance, I better be starting with something quadratic in the Yang-Mills amplitudes. And the same general arguments that I gave about identities between Yang-Mills amplitudes tell us that there has to be an equation of this sort relating gravity to Yang-Mills, so long as f is some polynomial in the Mandelstam invariance. Then you're guaranteed to have a syzygy. What is not guaranteed by the general argument is if that polynomial in front of the gravity amplitude is just unity, plus or minus one, depending on how we normalize things. Of course, we know that at tree level, such a thing exists. That's the very famous KLT relation. And that has been the basis for a huge number of papers and maybe even another subfield, that of applications to gravitational waves. So one thing you might ask is, what about one loop? I think this material people here know, so let me just skip over it. There are general formulas for KLT at all multiplicity, and you can, there's also, this is something you can do d-dimensionally, and this matrix has an interpretation, and you understand the string theory origin of it. So here I think you understand why this is happening. One thing I will mention is that the form, of course, of this kernel is not unique, and some of the so just as if there are syzygies of the amplitudes, there are also syzygies of products of amplitudes, and those syzygies give you the set of redundancies of the KLT matrix, something that I don't think has been actually explored that much in the literature. So the question you might ask is there a similar relation for the all plus amplitude at one loop? So if I were allowing general polynomial here, the answer on general grounds would be yes, but if I force this to be just a constant, then it's not clear. So you want to write it in exactly the same form as at tree level. So the gravity amplitude would be equal to some quadratic in the Yang-Mills amplitude with some kernel that is a function of Mandelstam invariance alone. Obviously, since we're at one loop, it has to be of one degree higher than at tree level. And we've checked that the answer is yes for n equals 4, 5, and 6. In a certain sense, there's uniqueness properties at 4 and 5 point. At 6 points, there's kind of an irreducible set of syzygies that are not easy to remove, which means that we also don't have a simple form yet. And no guarantee a simple form exists, and of course we don't know what happens beyond 6 point. But at 4 and 5 points, there's actually a very simple structure. Basically, you can restrict the non-zero elements of this matrix to when there's two common poles between the permutations rho and sigma, and then you get factors of those two common poles, and then there's some linear function in the Mandelstam invariance that gives you so the matrix in the 4 and 5 point case has a very, very simple form, and 6 point remains to be.
You learn anything by comparing this matrix to the tree level one?
it's not, we're not really at the point of doing that yet. It's not, as far as I can tell, it's not the inverse of any scattering matrix in a field theory, but this, there could be. The answer is I don't know. Maybe there's some interpretation like that, but there's nothing that has jumped out as obvious to us. And it's so this form is also the uniqueness is helped by the fact that, or I should say, it becomes unique at 4 and 5 points when you make it manifestly both symmetric, and at 6 points that's no longer true. So because they're in so the syzygies of products of amplitudes, there are no manifestly both symmetric non-trivial ones at 4 and 5 point, but 6 and beyond there are, and that complicates finding a simple presentation because there's some numerical work involved, and that means you're using random momentum, and then random kinematics kind of gets caught into these things. So that brings me to my summary slide, and the main message is that scattering amplitudes have to have lots of new identities that people weren't thinking about before. And it turns out that, at least in the cases that we've looked at, these scattering amplitudes, these extra identities, are actually relatively simple in polynomial degree, and sometimes even simple in their form. And if one thinks beyond the examples I've looked at here, for similar reason, at the very least, for rational terms in higher loop amplitudes in QCD or in ordinary gravity, there have to be similar sorts of identities, and also for the coefficients of integral functions in higher loop amplitudes, there have to be such identities, and of course that's not a proof that they have simple form, but I think they are likely to. So thank you.
Do you have any speculation what the heck's going on here? Like,
Why they're simple?
Yeah, why they're simple, or why exactly where it's coming from?
No, I mean, I think it's kind of like, where is BCJ really coming from? But that's kind of that question on steroids, because
we don't understand that.
no.
I just before I asked you the question, I was thinking about that. It's not going to be a great question since we don't actually even know what BCJ would.
It could be that they share a common origin, and it could be that they're different, because the thing that's more complicated here is that they're helicity dependent. These syzygies are helicity dependent, but they on the other hand, what is true is that if you know the syzygies for the simplest non-trivial case, so let's say if you know them for the 4-point amplitude or NMHV, of course, there's nothing going on in 4 and 5 points. If you know it for the 6-point amplitudes, actually, I guess if you, that's not good. There actually, you can also build things up from the 4-point amplitude, but there may be cases where you need to start from a slightly higher point. But once you know the basic structure, then everything else is ultimately determined by factorization. And in the case of non-trivial loop amplitudes with integral functions, you'd probably add additional equations from cuts, and then you have this set of identities, and I think it's interesting to ask what are the kinds of what can you do with them, and that's something we're starting to play with.
Can you, like, for loop calculations, can you think of something like manifestly canceling some spurious poles or reducing the orders of spurious poles? Like when you start, like in pentagon function, or like 5.2 loop, for example, you start out in QCD and it's a horrendous mess, right? The coefficients are terrible. in front of like the pure function basis, let's say. And then maybe you can use some of these.
So this could be, it could be a guide to finding I mean, these are generalizations of functions that Lance, Svi and I wrote down, also Nigel Glover and John Campbell at One Loop, where you kind of judiciously make combinations of boxes and triangles to remove some of these singularities. So this could be a guide to finding them. That's it could be a help there.
Any more questions? Thank David again. We even have cookies.
So maybe you can, but